the idea which led Riemann to a definition of a manifold, which is now, of course, the basic concept of geometry. So Riemann considered things like Riemann surface of a function. Suppose you have a function which is given by in a parametric way, p of xt equals 0. P can be a polynomial or it can be an homomorphic function. Suppose it is at least it's polynomial in T. Suppose it's actually a polynomial in T, polynomial of degree T for all x. We can consider things like T third plus some polynomial of x T2 plus some polynomial of x T plus the third polynomial, something like that. Then for each x, this equation, the equation p of xt equals 0 has three solutions. So for each point in x, you have three different t which are solutions of this equation. Of course, these solutions will change in time. Moreover, they can, at some point, they can, they would be equal. So it's there's no such functions which takes you some x and gives you three equations, three solutions of the equation. It gives 3 points on C, but these 3 points can coincide. And this is what is called branched cover, because it's like a cover in the sense that for general point, when you have 3 different roots of this equation, it gives you 3 branches of your multi-valued function. You can consider this as a multi-valued function. But in special points, there could happen things like, for instance, t squared equal x, and the corresponding Riemann surface is given by its branches in 0. And you cannot choose a single branch of this multivariate function because there are 2 square roots which would be exchanged by a monodromy around the 0. So this is why it is called branched. If you remove the singular points, the points where it is branched, which are also called branching divisors, then it will be a cover. But still you don't have, it will be a multivariate function, but you can't choose a branch of the function because the branches will be exchanged by monodromy around the singularity. What I'm going to tell today is a similar result for any algebraic variety. But it can be told in the language of commutative algebra. In fact, it will be proven in the language of commutative algebra. The idea is that if you have an algebraic variety in Cn, then there exists a change of coordinates such that the projection to Ck is branched cover. It's finite and surjective. This doesn't work for all coordinates, but it works for most coordinate system. You can have such a projection. And then this would imply that A is like a branched cover of Ck. Okay, I'm reminding you about finite morphisms. If you have A containing, well, B containing A, the corresponding, B is finite over A if B is finitely generated as a model. And what we had proved that if you have a map from X to Y, and OX is finite over OY, then the first, the number of preimages is finite. Should I explain that in more detail? It was something we did a lot. And the second is that if F is dominant, and this is equivalent to A, so generally speaking, you would have the map of Y to O of X, any map, any homomorphism, but it should, for dominant, this means that it's injective. Then F is surjective. So this is what happens in that case, because if you have an equation, it has precisely 3 solutions of this type. If it's dimension, it's degree D, it has precisely D solutions. Some of them can coincide, but in a sense, there are always the same number of solutions. At least it can happen that there are no solutions. Okay, so should I repeat this, or is it okay? Good. Now I'm going to produce an example, which is quite nice, and it's instructive in the sense that, in fact, all finite math has the same nature. Well, more or less. So suppose you have there was something we had already done. Suppose you have G, finite group, acting on R, and then you have a map from the invariant, the set of invariant elements in R is mapped in R, and I would prove that it is, in fact, dominant and finite. So G finite group acting on adding R by homomorphisms. So by automorphism, because it's a map from the ring to itself. Okay, and then you have a corresponding map from of affine varieties R to spec RG is finite and dominant. And this means, of course, that equivalently RG is a subring in R. And the first is actually clear because it's a ring of invariants. And the second is that R is finitely generated as RG model. So this is, I just repeat this this geometric statement in algebraic terms, equivalently to this geometric statement. Okay. And the proof is not very hard, so proof. First, we need to show that it is, well, it is clear that it is dominant, because dominant is precisely that it is injective, and this is injective by construction. So dominant is easy, and finite type is finite as the model is harder. So you have G inside G, any element, and you have polynomial map PG from R to itself. And now you have R inside the R, any element, and you have the following polynomial. P of t is equal to the product for all G inside the group G of t minus G of R.
Do you assume that the group is finite?
Yeah, of course. Group is always finite. Here.
Because the statement means that so the ring of invariants is always finite dimensional.
Well, not really finite dimensional, but it is finite as, so if you have the ring R, it's finite as R of G model. Yeah, sorry, it's
probably not true.
Sorry?
But for general group, it's probably not
For general group, it doesn't make sense because, well, it's definitely false and doesn't even make sense because I mean, this is algebraic geometric statement, and this geometric statement actually uses that G is finite because we proved that the ring of invariants is finitely generated. It's Noether theorem, and of course it's false when G is infinite. So the statement, the geometric part of the statement doesn't make sense, and the algebraic version is wrong. Okay, so you have this polynomial. It's a polynomial of coefficients in Rg, because if you act by G on this product, it will be G will just exchange some of the factors in the product. So it's G invariant. P of t is G invariant, so its coefficients are in the ring of invariants. And this implies that R is a root of monic polynomial with coefficients in R of G. Yeah. And then last time we had a theorem that in this situation your finite the corresponding morphism is finite. Okay, so that's it. So it's finite because all its elements are roots of the morphisms. Roots of monic polynomials. Okay, so the definition. So I give an algebraic definition of the quotient set, something that everybody knows from, as a set. But I will explain why it is equivalent to the our usual notion of the quotient. So suppose you have R is a ring with action of a finite group G. Then, and X is spec of R, then X quotient by G is spec of Rg, of the ring of invariants. So this is our definition of the quotient. I'm going to show that this really works in the sense that the set of points of this quotient is the same as the set of orbits of z action on x. But before, I'm going to give you a couple of examples so you can see what happens. So the first example, you have x is C2, and z is z by 2. Acting x goes to minus, well, xy goes to minus xy. Minus x minus y. This kind of action. Then clearly, the green source x is spec of c of xy. Now, the functions which are invariant under this section is precisely even functions. So, xg is spec of c, and you take xy, and you take even functions, polynomials of even degrees of x and y, and this is the same as spec t1, t2, t3, quotient by t1 by the relations t1, t3 is equal to t2 squared. So let me explain how it happens. So our t1 is x squared, t3 is y squared, and t2 is xy. First, clearly we have this relation. Second, it's clear that all even functions are generated by these three monomials. And the third is that if you have some polynomial relation between even degree functions, it's all expressed through these relations because it's polynomial. It's not hard to say. So this is really the quotient. It's not obvious that the set of points in this set of maximal ideals in that ring is the same as the set of points in C2 up to plus minus 1, but it's not really hard to see. In the next slide, we shall see that in general situation. Let me give you another example. So this was the first example. The second. We take x is c, which is spec of c of t. And as our z action, z is z by nz, and it acts by rotation. So t goes to square root of, well, epsilon t, where epsilon is the root of power n, primitive root of 1. Primitive means that it generates all other roots of unity. Okay. Now, if you have a polynomial p of t, and you replace t by epsilon t, the polynomial coefficients, so if it is sum of ai t power I, then this generator, let's call it gamma of p of t is equal to sum ai t power I epsilon power I. So all gamma invariant polynomials are polynomials of t power n. So, in other words, if you take C of t G invariant, this is the same as C of t power n. Make clear? So this means that, in fact, the quotient of C by rotation is against C. Something that we know if you think of the this branched cover of C by C, like n-sheeted branch cover, which is a Riemann surface for a root. So if you have this equation, t power n equal to x, and you take its Riemann surface, the corresponding branched cover, it will be precisely C. So your map from C to C takes t and puts it to t power n. And this is n to 1 cover, which corresponds to this precisely this branched map.
Modify this example a little bit. So if we just consider reflections in one axis, so not minus x minus y. But
It will be a product, if you have two reflections, it will be a product of two these branched covers with n equal 2. So reflection x t goes to minus t is this kind of map for epsilon is plus minus 1. And if we have two of them, then it will be just product of two of them. So it will be, if you take the quotient by reflections going to t to x goes to minus x, y goes to minus y, this will be again C2.
But there will be probably the root of minus.
Yeah. So minus, no, it will be root of 1.
Again.
Plus minus 1 is root, z by 2 is plus minus 1. And this is, you just put epsilon equal to minus 1.
Yeah.
Yeah, and in fact, there is a more general result that if you have a group generated by reflections, then the quotient is always smooth. If you have a group generated by reflections, acting on Cn, the quotient is always smooth. So the quotient, it will be precisely like in that case, or in case of C2 with two reflections, the quotient is smooth. But of course, this is actually if and only if result. So if you know that the quotient is smooth, the group is generated by complex reflections, which means that there are automorphisms which have fixed codimension 1 complex subspace. Okay. So now let me give the motivation for this definition, which says that the number of orbits, the orbits of the action is precisely this quotient, g by x by g, is precisely the set of orbits. As a theorem, suppose that G finite group acting on R, we have the corresponding finite map, spec of R, it's G quotient, RG, and then phi, this is called phi of x is equal to phi of y, if and only if there are points, x and y are points in say x. So this is equivalent to x and y in the same G orbits. So indeed, the quotient space is a space of G orbits. So this is a statement which I'm going to prove now. Is a statement clear? The proof is sort of straightforward. And this is an example of a finite dominant map. In fact, this is a general example. I mean, you can, if you think about that, you can use Galois theory and prove that more or less all finite maps are quotients of that map. So this is essentially the only example of finite map you can find, assuming something with a bit of extra assumptions, like normality. Okay, so proof, step 1. It's one direction. So if you have two maximal ideals of R which are G conjugated. So you have M1 and M2. These are ideals in R, maximal ideals, which are G conjugated. So they belong to the same G orbit. Then, of course, M1 intersected with R is equal to M2 intersected RG with RG, clearly. Because G acts on this intersection trivially, so it maps this ideal to that ideal. On the other hand, you have this nice, then a phi of, so what is phi? Phi is just intersection. So if you have an ideal in R, you intersect it with RG and obtain an ideal on G, this is your phi. Then phi of M1 is equal to phi of M2 because this is intersection M1 intersected with RG, and this is M2 intersected with RG. So this means that if you have 2 points in the same G orbit, they are mapped to the same point in RG. So phi of G orbit is a point. Am I clear? 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 Step 2. Okay, so now that you suppose you have an ideal in M in R. So it's a maximal ideal in R, G. Then you can take M R and take its G invariant part, and it will give you M. This is a lemma which we had it in lecture 6 when we proved this Noether theorem. It's not hard because you take all elements of M with coefficients in R, and you take the G invariant part of these coefficients, and this gives you precisely elements in M. So this is not hard. It's just projection to G invariant. Okay. Then you have a G is equal to RG quotient by M, where A is by definition equal to R times over RG quotient by M. And of course, by the standard arguments, this is the same as R quotient by MR. So then if you take invariant part, this just means that you project to invariant part, but M projected to invariant part gives you M, so RG gives you R projected to G invariant part, it gives you RG quotient by M. The projection is, of course, not multiplicative, but it's well defined. And it's linear under any G invariant, under implication by G invariant element. Okay. So now we're almost done. Yeah, you need, now you should I'm reminding you what is the preimage of a point. So step 3, A quotient by N. So N is inside A is a nil radical. A is defined here, nil radical. Then this ring, spectrum of this ring is phi minus 1. Phi is our quotient map. Phi minus 1 of M. This is something which we had already several times. Okay, so points of phi minus 1 of M are maximal ideals in the ring A quotient by N, or the same as maximal ideals in A, because all maximal ideals contain nil radical. Step 4. Now we should use that G. In step 2, we prove that AG is A. Yeah, sorry. It's A here. It's R G quotient by M. But this is algebraic variety, this maximal ideal, so this is C. Yeah, and the same argument, of course, implies that A quotient by N, G invariant, is the same C. Because there are no nilpotents there. But then A by N is Artinian ring. It's fine dimensional. A by N is Artinian. This means that A by N is direct sum of fields. And then we know what is automorphism group of this algebra. This is something we had already. It exchanges the idempotents. And the idempotents generate the C. Like primitive smallest idempotents, which is just generators of C. So if A by N G is equal to C, this implies that G acts on the summons, direct sum of C, transitively. If it didn't act transitively, there would be an extra invariant, like a sum of them, and there would be something like C2 in the invariant, in the quotient, in the set of invariants. So it has to act transitively, but this implies that G acts transitively on the set phi minus 1 of M. So preimage is precisely an orbit. And this finishes the proof. Was I clear? Okay, so this classification of Artinian algebras, it's really useful all the time. Okay, now I'm going to tell you about this projection. And before I'm doing that, let me tell you about transcendental extensions. It's really part of, again, the theory of field extensions and Galois theory. So it's something that is in the first step in most books and algebra of fields. Okay, so did I have the definition of transcendental extension? I think I have it. Well, let me define it because the definition is not here, but I think we had it. So definition, suppose I have k over k small, field extension, it's called purely transcendental, if k is equal to k small of two rational functions. Sometimes you include the infinite rational function, sometimes you don't. It doesn't really matter because it's something which almost never happens. Yeah, and the first claim is something which we had, in fact, in the first lecture. So claim, suppose you have k over k, where k is generated by one element. Is generated by x inside k over small k. So it's you take this x and you take all polynomials or fractions or of this x, and so that it becomes a field. Then either k is equal to rational function, so it's purely transcendental, or k over k small is finite. Okay, so how it happens? Well, if it's finite, then you have a polynomial. It can be rational functions, but suppose it's not finite. Then there's no polynomial relations on x. There's no polynomial which vanishes. So the ring of all polynomials of x is, in fact, embedded to the field k. And then its ring of fractions is also embedded to field k. So it is really rational functions, which are just the ring of fractions for the polynomial ring. Am I clear? Something that we have. It was on the first lecture. Okay. Now we have a simple lemma. You have k over k small is finite. Then you take rational functions of a variable t over a small k, also the rational functions in variable t. And this is also finite. You don't really need, for the proof, the primitive element theorem is not really required. There are proofs which don't use it, but still it's easier to prove it using this theorem. So I assume that k big is k small of alpha were by primitive elements. Alpha is primitive element, and this is primitive extension. Okay, we proved this theorem, so it's okay. And this is alpha is a root of reducible polynomial P of z. In K small of z. Okay. Then we can use again the standard product theorem, and we obtain that K of z, well, K small of z quotient by P of t multiplied over K small of t by K big of t. This is precisely our extension. Sorry. K of t. So we sorry. Of course, here and here. Yeah, so this is by definition, of course, I'm doing something bad, sorry. Yeah, we are interested in K of t. K of t, which is equal, obviously, by K of t multiplied over K small by K big. And this is equal to K of t multiplied over K small by K of z quotient by K of z quotient by P of z. Because this is precisely our K big. And then we apply the standard result about tensor products, which gives us that this is K of t of z quotient by P of z. We exchange these two variables and obtain that it's K big of t. This is it. So this is very formal and very trivial. Was I clear? Again, we want to have this field to have it as a finite extension of the field K of t. And we represent it as a finite extension in that form. So it's K of t quotient by a polynomial.
Finally, we got K big of t.
Sorry?
Finally, we got K big of t.
Yeah. So I start from K big of t and obtain this K big of t, which is K small of t of z quotient by a polynomial. So it is really a finite extension of K small of t. Okay. Now we need to have a transcendence basis. It's a bit like usual basis. So suppose you have K definition, K over K small extension, not necessarily finite, and T1 dot Tn inside K is big. And suppose that K big over K small of this, we take rational functions of T1, Tn, is finite, and k small of T1 dot Tn is contained in k big. So this means that these elements have no algebraic relations. They call T1 dot Tn are algebraically independent. They have no algebraic relations because this subfield is precisely this field of rational functions. There are no polynomial relations which vanish. And then T1 dot Tn is called transcendence basis. In k big. So k big depends algebraically on these variables, which are all transcendent over k small. So you have purely transcendental extension, and you have finite extension over this purely transcendental extension. Okay. So, and the point is that you can always have it. So it always exists. If you have a finitely generated, okay, maybe it's in this next slide. Yeah, first, let's notice that it always exists. So remark, T1 dot Tn always exists if k big is finitely generated as a field over k small. How to prove it? Well, proof. So either if k big over k small is not finite, it contains a transcendental element. This is something we already had. So if an element can be either algebraic or transcendental, so it contains, is not finite, contains, k contains transcendental element. Transcendental element. So you have k of T1. Okay, you don't even actually need finitely generated for that. The proof works. But you would have infinitely many if it's not finitely generated. So let's remove finitely generated. It just always exists. Okay, so then you add, then k big will be finite over k of T1, or it would contain transcendental element. In the second case, we just add transcendental element to this, and T2 will be our transcendental element, and we repeat. At some point, this procedure will end, and you would have no more transcendental elements, or you can take a union and apply its sort of lemma. In the end, you will obtain lots of transcendental elements with no algebraic relation between them, and then k will be algebraic over this. Well, maybe not finite, but algebraic. So let's see. Algebraic is different from finite. It's like algebraic closure. It can be infinite. So for finite extensions, this always work, and for infinite, you have to do, well, if it's finite, this will work. If you happen with, if it's really infinite, you can need to take a closure, and then you would have all elements of k algebraic over this closure of all these transcendental elements. Anyway, it's transcendental basis. But we are interested not only in the infinitely generated things, so it's this theorem 1, which I'm going to state now. So you take an algebraic variety with irreducible non-zero divisors. So it's like finitely generated ring without zero divisors. So K of X is ring of rational functions on irreducible algebraic variety. This is geometric language. In algebraic language, it's the same as fraction field of a finitely generated ring without their divisors. Okay, and you have S. Yes, we suppose that T1 to Tn are generators of this O of X. This is our finitely generated ring. Then there exists T1 for some subset of variables. So there exists finite subset S inside this finite set T1 dot Tn, such that T1 well, all elements of S are algebraically independent. All Si inside of S are algebraically independent. And then K of X over C of T1 O S1 dot Sn. So these are elements of S is finite. So this gives you a transcendental basis. You can choose transcendental basis among the generators. Okay, the proof is essentially trivial. So proof uses induction. Induction in the number of generators of the ring of X. This is our ring of regular functions on X. So you have a subring A inside O of X generated by T1 dot Tn minus 1. And then you have a subset of transcendental basis. So basis of transcendence, let's say T1 dot Tk. It's a transcendental basis in this ring of this field of fractions. By induction, we can assume it always exists because when this is one variable, it's already proven in the beginning. So if it's extension of one variable, it's either purely transcendental or algebraic. In the second case, it's finite. So when there's just one variable generating, we already have it. Okay, so now we are interested in Tn. So either Tn is algebraic over A. In that case, then O of K over A is finite. Or Tn is transcendental over A, then C of T1 dot tk Tn it's a subring, subfield in K of O X. And K of OX is finite over A of, well, it's finite over C of T1 dot T1 dot Tk Tn. Because this happens because O of x is equal to A of Tn. This is just polynomial ring. And K of O of x is K of A of Tn. And this is something we know, it's finite over a C of T1 dot Tk Tn. This is something we proved. If you have a finite extension, then the corresponding fields of rational functions are also finite extension. So this follows from that lemma I already given. Okay, let's have a break for 5 minutes. Temos intervalo para 5 minutos. nice geometric interpretation. Yeah. Which is the following. You have a map. You have your transcendental elements, algebraically independent elements, T1, dot, 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 T1, Tn inside O of x. This gives you a map from polynomials, which is injective. Since they're algebraically independent, there are no algebraic relations between these variables. And of course, this gives you a map from x to Cn, which is dominant. So what we proved now is the following theorem. I'm just restating this theorem, theorem 1, in the geometric terms. Let x be algebraic affine variety in Cn. I remind you that when we choose this transcendental basis, we could choose it in any generators. In particular, we can just choose coordinates as generators. Then there exists a subset of coordinate projection, x to c power d, such that k of x is finite extension of k of c of d. So this is our variables, which are algebraically independent. They give a transcendental basis, and this is the ring of the field of fractions of field of rational functions on x. What I'm going to prove now, the idea is that not only this would be finite extension, but you can also actually have it O of x to be finitely generated as O of Cn model. This is what we need. It's highly less trivial, but obviously, if it is finally generated of O Cn model, then you would have this finite extension as well. So this is halfway to, it's a part, several steps towards this purpose. Questions? I don't think it can be used there. But who knows? Okay. So this was our purpose. We want to have a finite projection from a reducible affine variety to Cn. And of course, it won't work generally. You need to change coordinates. For general coordinates, it just won't work. Okay. So what when the projection is finite? So remark. You have x inside Cn, and you have projection to CD from x to CD. So there are just coordinate projection. It is finite. So suppose it's a coordinate projection to the first t1 dot td, to the first d variables. If it's not the first, we just rename the number them, d coordinates. Then pi is finite. If and only if t d plus 1 dot t n are all roots of monic monomials, of monic polynomials on O of x. But all elements of O of x are actually, on t1 dot td in O of x. So you want to have all coordinates in x to be a finite type. They should be expressed as roots of monic polynomials in these variables where you project. This is a definition of finite morphism. It's finite if these are finite generated elements. When these guys are monic. Okay. So now claim. Yeah. So I would do extra assumptions, doing the renumbering the variables. So just to fix the notation. So theorem. So suppose you have x in Cn, z1 dot zk are coordinates functions on Cn such that k of x, this is the field, and then you take it over C of z1 dot zn is finite extension. This is something we already have. By theorem 1, such after some, CD or CK. This extension exists. Yeah. Then, for general, then there exists a coordinate change, a linear change of coordinates, So you take z I prime, which is equal to zi plus lambda I zn. This is a linear change of coordinates, such that zn is finite. This means that it's a root of monic polynomial over C of z1 prime dot zk prime. Yeah. Okay. And of course, this implies that the projection to the first key variables, well, if you do it for all, in fact, we can choose lambda I generic. Lambda I are general complex numbers. And we can do induction, like do the first variable, the second variable, and so on, among the variables which are not in the first k variables. You can replace zi by this linear combination repeatedly, and you obtain that all variables except the first k are finite in the first k variables. This would mean that the projection to the k variables, to the first k variables, is finite. Am I clear? So we want this O of x to be finitely generated over polynomials. And how we do that? We just do a linear change of the coordinates repeatedly, so that all the first variables are algebraically independent, the first k variables are algebraically independent, and the rest are roots of monic polynomials. This is how you do this reduction to finite. Okay. So let's prove it. The proof is, it takes some work. It's not long, but it takes a concentration to have it, to understand it. Okay, so first I do it for n. I ignore the variables between the k and n. But what we know is that there exists algebraic, this is find extension. So there exists a polynomial. There exists a polynomial p, z1 dot zk, zn. It's polynomial relation. Polynomial relation. Non-trivial. Non-trivial. Positive degree in Zn. It exists because everything, any element in this field is a root of polynomial in that field, and then you just do a common denominators obtaining the polynomial relation. Okay. So where we take, it's a polynomial in all these variables, take p of minimal degree. Take p of minimal degree in all these variables. In z1, zk, zn. So I take the sum of degrees in all of them, and I take the minimum. It exists. And it is non-trivial in n because the first k are algebraically independent. So there is no polynomials which can vanish on the first k variables. This means that you have to include n. Even if your degree is minimal, it's still there. Now, I already fixed this polynomial of smallest possible degree, and I take its graded component. So take f x1, xk, xn. This is homogeneous. So take fp homogeneous of maximal degree. Again in x1 dot xn. So I take, I decompose this polynomial p into a sum of graded polynomials in these variables, and I take the homogeneous component of maximal degree in all these variables. Okay. And I define q. Q is a function. So this is step one. Step two. define Q. It depends on F. Q of Z1. So I define Zi prime, Z1 prime dot Zk prime, Zn is equal to F of Z 1 plus lambda 1 Zn, Z2 plus lambda 2 Zn, and so on, up to Zn, where Zi prime is equal to Zi plus lambda I Zn. It's also homogeneous polynomial. It's a homogeneous polynomial which depends on lambda. Okay. Now I write Q of 0, 0, 0, 1. Q of 0, 0 k times and 1 is by definition equal to F of lambda 1 dot 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 lambda k and 1. It is non-zero for lambda general. Because if it is 0 for all lambda, look, it's a homogeneous polynomial. Then it is 0 for all variables, it's just 0. So it can't be 0 for general lambda. I mean, the 1 here, you can't put anything because it's homogeneous. So if it is 0 for all lambda, this is just 0 polynomial. It vanishes everywhere. Okay, so it's non-zero. And then you have, if it is 0, then the top degree polynomial, the top degree component of this polynomial p is non-zero, is 0, which is impossible because we choose p as minimal possible degree polynomial, which satisfies, which vanishes on these variables. If this homogeneous part is 0, this means that you can choose a smaller degree polynomial with the same property. Good. Okay. Then it is non-zero. And we choose this lambda, we choose Z prime with this particular lambda prime. And we have step 3. So you have polynomial Q of Z1 prime dot 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 Zn prime 1 T is homogeneous of degree D, same degree as this F, and it is monic in T. In T, because, look, you have this if you put all these guys are equal to 0, then this is non-zero. So if all the I are equal to prime are equal to 0, this is still non-zero. So it is because Q of 0, 0, 1 is non-zero. So the top degree component with respect to T is non-zero. Then it is monic. So this is monic. And then, of course, the same is true for the top degree of P. So P of Z1 prime dot 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 Zk prime Zn is monic in Zn. So if you put 0 here, everywhere, you will have 0. Okay. And then Zn is finite over as an, so this coordinate as an element in O of x is finite over Z1 dot dot Zk prime. Okay, so this is a computation, essentially. So what you do, you replace your variables in such a way that the this new in the top degree of your polynomial on this vector becomes non-zero. It's not hard because the top degree can be 0, and if you have homogeneous polynomials, it's non-zero in one direction at least, unless it is 0. So you have this. This gives you monic polynomial, which is a root, which has a for which the last variable, your Zn, is a root, and then it is finite. Then you do the same with respect to all variables repeatedly, choosing the general linear change of your variables, and you obtain this finite extension. Okay. So now I'm going to give you the more geometric interpretation of this result. So the first observation is something we had several times already. So you have 3 finite extensions. So remark. You have A inside B inside C, no rings without their divisors. And C is finally generated as B model. B finally generated as A model. Then C is finally generated as A model. So to see that, you choose B1 Bn generators of B over A. And you choose C1 Cm generators of C over B. Then each element x inside C is written as x is sum of Ci Bi, right? So Ci beta I, where beta I belongs to B, some elements. This is because Ci generate C over B. And then each Bi is written as a linear combination, sum of Ci, and then you express each Bi through this Bj, alpha I, beta j, where alpha is inside A. Sorry, beta is not here. I expressed each beta I through B and alpha ij. Right. These are elements in alpha I, j are in A. So I reduced everything. First I take x. I expressed x as a linear combination of ci and beta I, but beta I and b. And then each of beta I expressed as a linear combination of alpha I, j in A, and bj, which are generators of that. Something we used a lot, but I thought that we really should repeat this. Is it clear? Okay. So what we just obtained is that we take a projection we have x in Cn, and we take projection pi from x to Cn minus 1 to coordinates z1 prime dot zn minus 1 prime. Well, we could take smaller number of coordinates, but anyway, this we definitely have this finite. In fact, yeah. So you can do it up to k. K, and then you have is finite. Okay. Corollary. Every finite. So you do it repeatedly, one variable, another variable, and you use this. So each projection gives you an embedding of the corresponding rings. And each of the steps is you add a variable which is a finite, a root of monic polynomial, so it's finite on each step. So you do it repeatedly, and then you obtain every finitely every affine variety. Every variety admits a finite projection to C power D. Finite dominant. Finite dominant. Okay, so we obtained everything as a branched cover over Cn. So this is all for today, I guess. Any questions? Why we use irreducibility? Well, you can do it with each component, in fact. But irreducibility is used because the proof actually uses that we have a field. So, in fact, you don't need that. You can just restrict yourself to each component, and then you can try to prove that if the problem is that we didn't, for rings, we didn't define finiteness for when you have, so in algebraic geometry, it makes sense to define finite map from non-reducible varieties. But in commutative algebra, it sort of doesn't make sense because you have ring as a subring. And then you want that to be, you use fields to define finiteness. So if you don't have fields, the definition doesn't make sense. The notion makes sense. In fact, we defined finite maps for affine varieties without this assumption of irreducibility. But the proof, at least, if the proof is commutative algebraic, we used only rings, and we assumed they're without z divisors. So it's a natural assumption that we have, it's irreducible. You can extend that to non-reducible. It's an exercise. More questions, maybe? Please. Sorry?
Is this another normalization lemma of the first version? It doesn't make sense over real numbers.
I think it should.
Because you didn't use it. But
I don't think I used anything. Of course, what I am always assuming that we have equivalence between geometry and algebra, which takes C.
yes, sure. But
Yeah, but I don't think we actually used it. So it seems that the whole proof will work over any base field. As long as your ring is finitely generated, you can always do the same like polynomial decomposition, this linear coordinate change, and you will arrive to the same statement. It's, again, a good exercise to think that through. Maybe any other questions? Was it clear? Ok. Muito obrigado.